Probability is the study of random experiments whose randomness properties are specified completely and precisely. For example, what's the probability that I get at least 7 heads and 10 independent flips of a fair coin is a probability question because we have agreed to assume the fairness of the coin and the independence of the flips. Establishing the relationship between probability models and real-world random experiments, like determining whether a coin is fair, is up to statistics. We will develop a suite of tools for answering questions about probability models before we turn to the study of statistics. One approach to answering probability questions is to use a set of basic probability manipulation rules. We learned, for example, that the probability that two independent events both occur is the product of their probabilities. This approach works well most of the time, but it does have its limitations because different ways of applying the rules can lead to different answers. In all such cases, at least one of the answers is wrong, of course, but the rule manipulation approach doesn't always provide satisfactory tools for identifying or understanding the error. Let's look at an example. Two sealed and indistinguishable envelopes contain money, one twice as much as the other. A contestant selects one of the envelopes and gets to keep the money therein. They choose one of the envelopes, but before they open it, they have the option to switch. Should they? On one hand, they have a 50-50 chance of choosing the higher value envelope no matter what, so the contestant should be indifferent to switching. On the other hand, if the amount of money in the initially selected envelope is X, and the amount of money in the other envelope is either 2X or 1/2 X with equal probability, then you could reason that the amount of money in the second envelope is 5/4 X on average. From that point of view, the contestant should switch. Mathematical probability is an approach to answering questions about probability using a mathematical model. In other words, we will introduce a mathematical object which represents a random experiment, as well as a dictionary for translating probability questions about the experiment to unambiguous questions about the object. We will take as our running example the simple experiment of 2 fair coin flips. In the context of a random experiment, an outcome is a possible result of the experiment. For example, both coins came up heads is an outcome. An event is a statement whose truth value can be determined based on the outcome. For example, at least one coin came up heads is an event. The probability of an event reflects our confidence that the statement will turn out to be true when the experiment is run. Events are independent if they have nothing to do with one another. Knowing whether one of them occurs gives us no information about the others. If a random experiment has a payout, then the expected payout is how much the experiment pays out on average. Let's make sense of all of these terms in the context of a mathematical model. We begin by writing down all of the possible outcomes, HH, HT, TH, and TT. We'll call the set of all possible outcomes the sample space, and we'll use the letter capital omega. If we want a variable name for one of the outcomes, we'll use lowercase omega. An event is a statement which is either true or false for each outcome. For example, the event at least one head is true for these 3 outcomes and false for this outcome. We can associate an event with the set of outcomes for which it's true, so we will say that an event is a subset of omega. We will think of probability as a single unit of mass which is distributed to the elements of omega depending on the likelihood of each one. In this case, there are 4 total outcomes, and since the coin flips are fair, it seems reasonable to believe that the outcomes are equally likely. Therefore, we will assign to each outcome a probability mass of 1/4. The function which tells us the probability mass associated with each outcome is called the probability mass function. Given the outcome probability masses, we can define the probability of an event to be the sum of the probability masses of the outcomes in the event. The map which associates each event with its probability is called a probability measure. The sample space omega together with the probability measure p is called a probability space. With these definitions, common ways of combining events correspond to common set operations. The event that E occurs and F occurs is E intersect F. The event that E occurs or F occurs is E union F. And the event that E does not happen is E complement. Saying that the occurrence of an event E implies the occurrence of another event F is equivalent to saying that E is a subset of F. Let's look at some basic properties of a probability space. First, the probability measure of the whole sample space is 1, since the sum of all the probability masses is 1. Second, the probability of any event is non-negative. Finally, if 2 events are non-overlapping, then summing their probabilities yields the same result as taking the probability of their union. This last property is called additivity. We will think of these as fundamental properties of a probability measure and show how other properties follow directly from these. For example, if E is a subset of F, then the probability of E is less than or equal to the probability of F. To demonstrate this using the fundamental properties, we write F as a disjoint union of E and F without E. Then the probability of F equals the sum of the probability of E and the probability of F without E. Since the second term in this sum is non-negative, we can be sure that replacing it with 0 reduces the right-hand side, or leaves it the same. The probability that an event does not occur is equal to 1 minus the probability that the event does occur. We can show this using the properties by writing omega as a disjoint union of E and E complement. Then additivity implies that the probability of omega is equal to the probability of E plus the probability of E complement. Since the probability of omega is 1, we can subtract the probability of E to get the probability of E complement equals 1 minus the probability of E. Now let's think about the random experiment term independent. How can we mathematically express the idea that knowing about one event, E, gives us no information about another event, F? We first need to make sense of updating our probability measure based on the information that an event E occurred. We will define a new probability measure which accounts for this information called the conditional probability measure given E. Clearly, our conditional measure should assign probability mass 0 to each outcome which is not in E, since we know that those outcomes did not occur. And since we have no further information about the other outcomes, we should keep their proportions the same. Since we have to keep the total mass at 1, this requires that we multiply each probability mass in E by 1 over the probability of E. So the conditional probability of F given E is the sum of the masses of the outcomes in F which are also in E divided by the probability of E. Multiplying both sides by a probability of E, we get that the probability of E intersect F is equal to the probability of E times the probability of F given E. It makes sense to say that F is independent of E if the conditional probability of F given E is the same as its original probability. This is true if and only if the probability that E and F both occur is equal to the product of their individual probabilities. If we're looking to model independent phenomena, we can obtain families of independent events in the following way. Suppose omega 1 P1 and omega 2 P2 are probability spaces. We arrange the elements of omega 1 and omega 2 along a pair of axes, and we make a new sample space omega by crossing these two sets. We multiply probability masses from omega 1 and omega 2 to get probability masses for these new sample space points. Then every column event is independent of every row event. For example, if we want to model a weighted die roll and a weighted coin flip, then we can use this probability space, and every event pertaining to the die roll is independent of every event pertaining to the coin flip. Finally, let's look at expected payout. Suppose that a player receives $1 for each head in the two coin flip experiment. Then they win 0, 1, or $2 depending on the outcome. We can see that the payout associates a number with each outcome of the experiment. In other words, the payout is a function from omega to the set of real numbers. We call such a function a random variable. We obtain the expected value, or average value, of the random variable by taking an average of its possible values. Since we want more likely outcomes to count more and less likely outcomes to count less, we weight this average by the probability of each outcome. We can find the expected payout of the two coin flip game by performing a calculation on the sample space side or here on the codomain side. In either case, we find that the expected payout is $1. We can now address the exchange paradox from the probability model point of view. Suppose that the envelopes contain x and 2x dollars, and let's take as our sample space x, 2x, and 2xx. In other words, the larger amount is in the first envelope or the larger amount is in the second envelope. The expected value of selecting the first envelope is equal to 1/2 x plus 1/2 2x, which is 3/2 x. The expected value of selecting the second envelope is 1/2 2x plus 1/2 x, which is also 3/2 x. So the contestant can't do better or worse than an expected payout, which is the average of the amounts in the two envelopes. In summary, we have set up the following dictionary between random experiments and probability models. The set of possible outcomes of the random experiment is the sample space omega. The probability of each outcome is encoded in the probability mass function m. The set of events is the set of subsets of omega, and the probability of each event is represented by the probability measure p. The event that two events both occur is their intersection, and the event that at least one of the two events occurs is their union. The event that a given event does not occur is its complement, And finally, two events are independent if the probability they both occur is equal to the product of the probabilities of each.